Hello, everybody. Welcome along to the last of our Women in Data month events. We've had a great month, actually. It's been really good fun across the whole of the month. Really good mix of talks and topics. And today is definitely going to be no different, that's for sure. In terms of a couple of quick announcements. As you'll have noticed, we are theming each of our months and try to bring you different type of content across all the different months that we have. Next month, we're focusing on customer growth and marketing data challenges. We'll be putting a link in the chat, so please do go check it out. Again, we're joined by some great companies and have some great content planned for you, so please do check that out. In terms of today, really looking forward to today's topic because it has a bit of an engineering leaning, which is something that's close to my heart. I spent 13 years as a DBA before I moved into founding Data Idols. So I do secretly always look forward to it when we have an engineering focused talk for you. In terms of today, we've got a talk on Spark optimization, building an efficient lakehouse with Databricks. Really pleased to be joined by Oleksandra, who's a solutions architect at Databricks. So Oleksandra, if I could ask you to turn on your camera and microphone, we'll welcome you to the stage. So hello, Oleksandra, how are you doing today?
Hello, I'm doing great.
Good stuff, good stuff. We were talking actually just before you joined. Oleksandra is based out in the Netherlands. So this is one of the hidden benefits of the pandemic. We can get great speakers to join us from all over the world, which is fantastic. In terms of Databricks, this is the first event that we're running with Databricks. Really pleased to have them partnering with us over the next 12 months. I know we've got plans to have them involved in our main Data Science Festival in November. We've got a few other initiatives ongoing with them as well, and this is the first time that we have them joining us and speaking today. So Oleksandra, thank you very much for coming and sharing your knowledge with us. So if it's okay, I'll maybe get you to share your screen just to check that you're happy. And then we'll go from there. And just as you're doing that, as ever, everyone, we do try to make these sessions interactive, and Oleksandra has very kindly said that she'll stick around for 10 or 15 minutes after the talk to answer any questions. So as ever, there is the Q&A feature within the webinar software. If you could put any questions in there as you go, and it's great to have you with us. So Oleksandra, that looks fantastic from my side. So if you're ready, I'll get out the way and leave you to it.
Yes, thank you very much.
Perfect.
And
have a good one.
Thanks. We'll try my best. Hello everyone. Today the topic of my talk is Spark optimization, building an efficient lakehouse. I would like to start with a little bit agenda to scope our discussion for today. So what I would like to cover today is basically what is Lakehouse architecture and how Spark fits into it, some Spark general concepts to refresh your mind, refresh your memories, and something that will be important for us during the main part of our discussion. Also, I would like to cover why it's important to optimize Spark jobs and key point of optimization. And at the end, I will wrap up it with conclusions, and we will have a Q&A session. I also would like to mention that please ask as much questions as possible, and if not all questions will be answered today, we can follow up on them later, and we can have a discussion later on offsite. I will start with introduction of myself. I'm Oleksandra. I work as a solutions architect at Databricks. I have a master in applied mathematics. I worked as a researcher, data engineer, and software engineer before joining Databricks. So my background is fairly technical, and a lot of these tools and techniques that we will be talking today, I talk about them from my own practice. As we are all in this Corona time, it's popular to mention your Corona hobbies, but unfortunately, I didn't get a new Corona hobby. I continued with my own pre-Corona hobby. I like drumming, and I play drums in a band. I also would like to cover who is Databricks. You probably all heard about Databricks as a company, but Databricks as a unified data analytics platform. And we have more than 5,000 customers and more than 450 partners all over the world. And Databricks are original creators of popular open source frameworks like Spark, Data Lake, MLflow, Redation Koalas. I will start jumping directly into Lakehouse architecture, what it is, why it's important, and how Spark fits into that. To understand what is Lakehouse, we need to start a little bit from the beginning. So you all are should be familiar with the concept of data warehouses. Data come in mostly in structural format, undergo some kind of ETL process, end up in a data warehouse in, again, relational format. It's mostly well-structured data, and the main usage of this data is BI and reporting on top of it. Data warehouses were super popular, and a lot of companies still use them quite often and quite extensively for the purposes of BI and reporting. But unfortunately, when the volume of data grows, when the variety and velocity of data grows, data warehouses are not ideal to process all this data. That's why naturally the concept evolved into data lake. What is data lake? Data lake is a data architecture that can handle all type of data, structured, semi-structured, and structured. You can store all kind of data. You can process different types of data, and besides typical workloads, it also allows you to have a data science and machine learning workloads and processes on top of this data. Although it seems like a huge improvement comparing to a data lake, because it allows you more, comparing to data warehouse, because it allows you more use cases, to run more use cases on top of your data. But data lake is a quite dangerous concept because of a variety of data that you have. So if you don't structure it correctly, if you don't pay enough attention to the way how you process and structure your data, you can easily end up with a data swamp, where basically you have all types of data, no one knows what it is, no one knows who put this data there, and no one knows what to do with this data and how to process it further. Lakehouse as an architectural concept derived from two of other concepts, from data warehouses and data lake, and it tries to take the best of two worlds. On one side, we try to have all types of data available in our data system. On the other hand, we would like to have all benefits of data warehouses, like consistency of your data, ACID transactions, schema enforcement, and other constraints that you would like to put on your data. So basically, idea is to combine the best. Of course, it's not easy. Of course, you need to be able to have this type of architecture, you need quite an important tool. You need a framework that will enforce all this type of things on top of your data, on top of structured, unstructured, and semi-structured data. And we do it with two things. We do it with Delta Lake and with Spark. What is Delta Lake? Delta Lake is an open source project that is used to build a Lakehouse architecture on top of data lakes. It enforces ACID transactions, it allows schema enforcement, it allows constraints, and all performance benefits that you can get from accessing data on data lakes. On the other hand, Delta Lake is leveraging Spark as a tool underneath. What is Spark? Spark is a unified analytics engine for large-scale data processing. And if you are in a field of data engineering or data science, you, in most cases, are familiar with Spark. You either use it yourself, or you heard about it, or you know other colleagues who are using Spark. And Spark is de facto a standard for distributed data processing. Although there are other frameworks available on the market, Spark is mostly widely used, and it's one of the most popular frameworks, and the first that comes in mind when you talk about distributed data processing. To scope our talk a little bit, I would like to talk slightly about Spark architecture. I'm not going into all details about all internals of Spark, because for two reasons. First, it's not really relevant for this talk, and second one, it's too much information, I would say. But what is really important for now is to understand general concepts about Spark. If you ever worked with Spark, you probably saw this diagram on the left as a connection between driver, worker, executor, task, and so on. It's this schema you can find in documentation for Spark, and it's quite the first things that you see in documentation of Spark. It's a nice schema, it is relevant, but if we're talking about optimization of Spark jobs, it's more important to understand the connection behind it. So connection between driver, job, stage, and task. I put a diagram here to make it visually, but what I would like to point out is that in terms of Spark, task is the main smallest unit of work. So basically, when you distribute your workloads, task is where actual work happens. So where actual data processing of some piece of data will happen. Stages is a logical grouping of tasks, and job correspondingly a logical grouping of stages. Although this grouping is not random, but what is more important to understand that the Spark is the task is the smallest unit of processing. That's why all our further discussion will go around actually tasks. But one step back, why it's important to optimize Spark. Spark is an amazing framework. A lot of people are working on Spark, and it's just fantastic. It should work perfectly. You don't have to do anything. Unfortunately, that's not true. Because we are talking about data processing, and we are talking about distributed data processing. One feature, well, I would say feature in quotes of Spark, is that comparing to other programming frameworks, it can not only fail, it can also just not finished. And if you ever work with Spark, you probably have seen this picture on the right side. When you have a job that is running forever, 47 hours, although it should have completed in 20 minutes, and you have one task running somewhere and not doing anything, you don't know what to do, it never completes. Another thing with Spark is that it has tons of features. And on the right side, you can see the features that are currently in development for Spark. And it's only in development right now. It doesn't mean that all other features that Spark has are not there. Amount of features that Spark provides, and amount of optimizations and different tweaks and tunes that you can apply to Spark is enormous. And of course, you can't know them all. And of course, if you have an inefficient Spark job, it can introduce extra costs. It's especially important if you're working in a cloud where you actually pay for every compute instance that you have and every compute times that you use. But even if you're on-prem or even if you're working on your laptop, maybe it's not extra cost, but it's extra time. What I would like to cover in terms of Spark optimization. I would like to cover the following topics: cluster sizing, how to choose the best cluster size, partitioning of your data and why it's important, filtering, how to do it correctly, UDFs, user-defined functions, and what's the danger of using them, join strategies. Join is one of widely used operations that you do on top of your data sets. And then I will go into specific settings that I would like to mention. I will start with cluster sizing. If I suggest you two configurations to choose from, one cluster with one node, and here I imply one core for simplicity, and 100 gigabytes of memory, and another cluster configuration with 10 nodes and 10 gigabytes of memory per node. Which is better? Okay, here the answer is a little bit obvious. We want to run our tasks in parallel. That's why probably the second configuration is better. But if I have another one, I have cluster with 5 nodes and 20 gigabytes of memory per node. How it compares to the previous one? And like in most cases with programming, it depends. When you're choosing a correct configuration of your cluster, and it's probably the first thing that you do when you start writing your Spark application, you need to understand how to make it more efficient. Of course, I will tell you for sure, there is no silver bullet. There is no ideal configuration that you should choose and stick to it, and it will run forever for every kind of workloads that you have. If you want to start with that, just try to remember the formula. One partition of your data equal one task and one core. Give your task enough memory to handle one partition of your data. This should be your starting point when you choose a configuration of your cluster. It doesn't mean that it wouldn't change with time. It doesn't mean that it's ideal formula, not at all. But it's a good starting point to select a configuration of your cluster. And of course, you might argue why I need to do it. I can allocate all resources in the world to my Spark application and it will finish in a second. Unfortunately, that's not a reality, and we all work in some kind of constraints. If we are talking about one partition, one task, let's talk about what is partitioning. When I mention partitioning to any of developers that I'm working with, I hear back a lot of questions about it. First one, why we need partitioning? Okay, this is quite obvious. We try to process quite a lot of data in a distributed fashion because it's faster. And because our data just doesn't fit into memory of one laptop or one machine. Another question that I hear quite a lot is, what if I don't know how my consumers of my data are going to access it? What if I partition it incorrectly? What if my strategy changes, partition strategy changes over time? And I don't know how to partition my data in general. I just have it and I'm happy with that. What you need to understand about partitioning of your data, we are working in a distributed environment. We try to distribute our workloads as much as possible. In this case, partitioning is always better than non-partitioning. If you don't know how to partition your data, start with generic fields, like partitioning by date, partitioning by country code, depends on your data. If you don't know how many partitions you want to get, start with ideal, in quotes, partition size of 100 till 200 megabytes. Of course, it will not be, again, it's not a silver bullet for all situations and all type of data and all type workloads, but it's a good starting point if you don't know how to start with it. And if you don't partition your data, you just make your Spark application, try to work with the whole data set as a one big partition, because this is how Spark will interpret your data if it's not partitioned. Another thing that is very important when we are talking about writing our Spark application and, of course, optimizing them is filters. What is filter? Filter is everything that you put into where clause or filter, if you prefer that flavor. If you work with Spark, you probably heard about the concept of pushdown filters, which is basically filters pushed closer to the source of your data, regardless of which format your data is stored in. Your filtering is applied to this data as close to the source as possible, rather than later in the process. Here I put two examples, and if you look at them, they look quite similar, except one line. On the right side, you have where clause with a column amount greater than 400. And the difference for this column is basically the difference of applying a filter and not applying filter. If you try to make your Spark optimal, your Spark application optimal, if you try to make your application run faster and use less resources, your goal should be also to read as less data as possible into Spark. That's why filtering is so important. But more than that, you should also check if your filter that you put into your Spark application is actually applied. And later on, I will show you how to see it in Spark through Spark UI and through Query Plan, how you actually can check it. If you heard quite a lot that you should apply filters, you should minimize the amount of data that you read in your Spark application, remember another thing to that. If you use filters as much as possible, but also check if they're actually applied the way that you want them to be applied. Going from there, another interesting topic that is that I hear quite a lot and that I see quite a lot in Spark applications is UDFs, user-defined functions. Everyone who works with Spark knows that knows what is UDFs, and if you're coming from a software engineering background, UDFs just look awesome. They're just awesome because this is the whole concept of software engineering. You have a small blocks of code. They're easily testable. They are independent. You can share it between teams. You can put them in the libraries or frameworks. It is just what you are looking for. But UDFs, user-defined functions, have one drawback, one backside of using it. Especially now when PySpark, so Python flavor of Spark, is much more popular within data science community and within data engineers as well. Using Python UDFs can be quite time-consuming comparing to, for instance, Scala UDFs. Why? Because we have serialization. Spark is a JVM-based framework. Underneath, it uses JVM. Python is a separate language, and Python is a black box for JVM. So whatever you put into your UDFs, in Python UDFs, it will be just a black box for Spark. Spark can't apply any kind of optimization, any kind of improvements to your UDF, because it just doesn't know what's inside. Besides that, Spark also needs to serialize your data twice. First, when it sends it to UDF, and then the second time when it gets their data back from UDF. That's why, because of that, the performance of pure Python PySpark UDFs can be much worse comparing to performance of Scala UDFs or just DSL, which is basically Spark functions itself. Here I added a comparison for exactly the same workloads, exactly the same transformations on the same cluster. And you can see a significant difference comparing of using UDFs in Scala and UDFs in Python. Okay, but does it mean that we need to rewrite all UDFs in Scala because it's more efficient? Of course not. You just need to choose something that works best for you. If you want to structure your code with UDFs, or especially if we're talking about data science workloads where libraries that you are importing into your Spark application exist only in Python, so they are just not supported by Spark itself, the things that you need to remember is minimize using Python UDFs, switch to Spark DSL, Scala UDFs, or Pandas UDFs, and as a separate type of UDFs, they leverage different mechanism underneath, and this will be more efficient. Especially if we are talking about UDFs for simple transformations. If you're just concatenating a couple of strings, or if you're just applying some kind of simple regex function, check if it's already available in Spark itself. And a lot of functions are, so you can just apply them from Spark, and it will be it is efficiently optimized internally in Spark, but it's also more efficient from Spark can leverage other mechanisms to use these functions. If you examine your code on in trying to make it more efficient, check if you are using UDFs for everything or if you're just using it exactly where it's needed. But we were talking about filters, and I promise you to show how you can see it in a Spark UI. And now you may ask me, okay, Spark UI, Spark does have UI as a framework. What kind of UI it has? And the interesting thing that a lot of, especially new users to Spark, don't know that Spark has a UI. And you actually has a lot of information. It actually has a lot of information that you can use from there, and a lot of information about performance of your application, and also a lot of information of how you potentially can make your application more efficient. On the right side, I included a screenshot from a Spark UI and SQL tab in Spark UI. where you can see a query plan. This is basically a visual representation of how Spark interprets your job, your application, how Spark understands what needs to be done. And if you, in a real Spark UI, not on a screenshot, but you can also get much more information from it just by hovering it or expanding on cells. And you can see amount of data that is participated in this operation. And just looking into that, and on this particular example, you can see that one specific table is basically just read 4 times in this particular example. Just visually examining it, you can understand that, yeah, maybe it's not the most efficient way of doing it. Maybe I can rewrite it. Maybe I can cache it. Maybe I can do something better, just not to read the same data 4 times. You can get to Spark UI from your Spark cluster, regardless if you're running it on Databricks or standalone, or even if you're running it on your laptop. You can still get access to Spark UI, and you can see how much information you can get from there. Now, I don't want you to go there and to understand everything, every single row or every single block on Spark UI. It can be quite complex, especially if you do non-trivial transformations and so on. But if you just know that it exists, and if you know that it can give you insights about your transformations, about the performance of your application, just go there, check it out, and see what information you can derive from that. And of course, you can use explain function from your code to get the same way, but in the same information, but in written format. I prefer visual on Spark UI because I like to see it rather than read lines of transformations that Spark is doing. Now, a little bit difficult part, because I would like to talk about join strategy. Join is one of the commonly used operation in data transformation. You have 2 tables, you have 2 data sets, you want to join them together, and you want to make it the most efficient as possible. Unfortunately, join is quite a heavy operation. It can take a lot of time. It can perform a lot of manipulation of your data, and it can actually not fit into memory and fail successfully at the end. What you need to understand about join strategy. First, Spark has multiple join strategies when you just write df1 join df2. Spark actually chooses which is the best way to join these 2 data sets. A particular information, which exact join type is used in your particular example of Spark application, you can see also in Spark UI, and exactly the same SQL tabs that I showed to you. What is important to know here? If you're looking on these join strategies, you can understand that there are a couple of them, and some of them are better than another. And of course, Spark is smart enough to choose the best strategy for you, for your particular data transformation. But sometimes you need to help Spark to do it a little bit more efficient. For that, you need to know what you're doing. There are 4 types of joins that I would like to cover in this presentation. It's a broadcast hash join, shuffle hash join, sort merge join, and Cartesian join. I show them here in the order from best to worst, but it doesn't mean that they are never used. It's just the best, the most performing one, but it's not always applicable to the amount of data that you have, or to the operation, to the size of clusters that you have, or operations that you perform. I will start with top one, broadcast hash join. If you have a small data set joining with a big data set, broadcast join is the best strategy that you can use. It doesn't require shuffle, doesn't require sorting. It's super fast, and it's the best of all join strategies that Spark has. On the second place, you have a shuffle hash join, which is join based on a hash table. Because of that, because Spark needs to build a hash table for your data, it can also lead to out-of-memory issues if your data is skewed. So basically, if your one partition of your data is much greater than other partitions of your data. But if you have quite evenly distributed partitions, this type of join can be very efficient. Another type of join, and it's mostly widely used join in when you join big data set with big data set is sort merge join. It's robust. It doesn't generate out of memory issues. It requires shuffle, it's sorting data, it's slow when you have a smaller data sets, but in most cases, it's quite a robust solution. Cartesian join. Avoid it as much as possible. It's basically joining everything with everything. There are very few situations when you actually need joining everything with everything. In most cases, you have some kind of join condition. If you want to understand what join strategy is used for your particular use case, go to Spark UI, go to query plan, and see in the fork where you see that two data sets are joined together, see there what type of join is used. You can influence what kind of join is used by using hints in Spark 3. You can also influence it by disabling or enabling auto broadcast join for Spark, and also disabling or enabling preferred sort merge join setting. So basically, if sort merge join will be used or not. The key takeaway from here that I would like to mention is that you know your data. You know how your data is structured and what you are trying to achieve with this data. You know your transformations. Spark can do its best to apply the most efficient join for the specific task. But sometimes you need to help him. Sometimes you need to put extra hint or extra information for Spark to make your join more efficient. As we were talking about a couple of settings that I mentioned on the previous slide, let's talk about others, right? Spark has more than 400 settings that you can configure, and it's only Spark settings. I'm not talking about product-specific settings, like I mentioned Delta at the beginning, and Delta has a lot of its own settings. Databricks, if you're running it on Databricks, there are a lot of settings that you configure there as well. Okay, we use different data formats. Every data format has some Spark settings that you can tweak and tune. Some settings are mutually exclusive. When applying one, another one will be not leveraged. The best practice that I experience in my day-to-day job is try to use as much default settings as possible, and then choose to change on the specific settings when you really know what you're trying to achieve and what the problem you try to solve. You can see what settings were changed by using again Spark UI environment tab, and you can see it here, and it shows you all settings that were changed. If your settings is not here, it's Spark uses a default value. Default values you can always check in documentation. But once again, if you don't know which settings to change, don't change them all. Don't try to apply all new features that are available for Spark, and you heard about them on conferences, and don't try to apply them all. Apply the settings that you know what they're doing and how to use them. Unless this is the Spark shuffle partitions. These settings should be changed almost always because the default value is too generic for any type of data set. So if you change only one setting set, then it should be this one. And now a little bit of examples that I saw in my practice, and you might see as well when you're writing your Spark applications. The first one is timeouts. If you look at an example on the right, you see that Spark executor heartbeat interval is set to 2 hours. I saw it literally in a code. It basically means, dear Spark, do whatever you want, come back in 2 hours if you have an error or whatever. I do understand where this setting is coming from. You have some kind of timeout issues. You try to solve it by just increasing timeout because it's what logically people do with timeouts. You try to increase it to the value when it works, but it doesn't actually work. It just delays your problem for a specific time. If you have a timeout issue, try not to just simply increase timeouts, but try to understand maybe it's, in most cases, it's something bigger covered by timeout issue. It might be a misconfiguration of your Spark cluster if you're running it on-prem or even in the cloud. Or it might be some kind of bad node failure, something fishy is going on with the network configuration of your Spark cluster. Another typical example that you can see quite often is taking broadcast under control. So basically what you do here, and this is example number 2 on the screen, you see here that we disable auto broadcast in Spark, and then we use a hint broadcast to enforce broadcast join. I mentioned before that the broadcast join is the fastest type of join. So it's basically sending your data everywhere to all executors. So you don't require any shuffle operation, and the join itself will be super fast. This is a good idea. It sounds like a very good idea. So I don't trust Spark. I will do it myself. I know better how to do it. But let's imagine that this particular example is running in a pipeline. And this particular Spark job is running every day. And your data set is growing over time for whatever reason. If you do auto broadcast, you're basically telling Spark, stop, I know what I'm doing. I want to broadcast it anyway. If your data size is growing and you still put a broadcast hint, your data will be broadcasted. Spark will try to broadcast it. But if the data size is too big to fit into memory, it will just fail. And basically, you will get just a one-day random failure of your whole pipeline just because you're using a broadcast. It doesn't mean that you shouldn't use it, but just be aware of what you're doing. Another example that happens quite often is using caching for data frames. And sometimes it leads to hidden mistakes. Caching is amazing. You're using it to just not read your data multiple times. It's nice, it's meant to be used. But if you are using it in the wrong place, you can actually break all optimizations that Spark provides to you. Like here in example number 3, you can see that we're using a cache in the middle just after reading our data and before applying filters. In this case, your filters won't be pushed down. So Spark will still read the whole data set here and then apply filters in memory. The whole, I don't know, 100 gigabytes of data will be read into memory just to apply these filters. If that's what you need, if that's your idea and that is what you need in your Spark application, it's fine. But just be aware of what it does and how it actually performs. If you use a cache, in this case, it will stop from pushing down the filters. Okay. We looked into a lot of techniques and a lot of things to process. How we can see it? Again, the answer is Spark UI. You can go there and you can see a lot of information. In this particular example, I would like to show you how you can see a data skew that in your data from Spark UI. First of all, you go to a job tab and you see that, okay, my pipeline, my Spark job that should finish in 30 seconds already run in 2 minutes. And only one task is running. Okay, it might be something fishy. You go inside your Spark, inside your active job, and you see a stages and the metrics for a stage. You can, when you run your Spark application, you can do all the clicks and you will see where all this information are. It is, and you go to the metrics, and basically there are metrics aggregated per task. And you see here, okay, all my partitions are more or less the same size, except the maximum partition, which is insanely bigger comparing to a median size of a partition. Okay, now you definitely know what's happening. Your data set is queue, so one partition is much bigger than all other partitions. You open an event timeline, again on the same stages tab, and you see, okay, it's definitely the case. All my tasks are already finished, everything is perfect, and one task is running forever. What you can do with it is up to you. There are a lot of techniques how to combat data skew. There are quite a lot of some settings in Spark that can help you with that. But to actually apply the settings and to actually solve this problem, first of all, you need to know that the problem actually is there, so that the problem exists. And this is the way how you can see it. It doesn't require extra manipulation with your data. It's just there for you to see. And it's only beginning. The things that we covered today is just a small portion of things that you can change, that you can configure, that you can know about Spark. And again, Spark is just a part of the ecosystem. Although it's a great tool and a great framework, it's just a small part of a bigger data and AI ecosystem that you will probably be working with. There are a lot of other frameworks in these ecosystems that can influence performance of your Spark application. The obvious example, you're reading data from any kind of storage. And if this storage is not performing good enough, if this storage is not giving you data fast enough, your Spark application will be not efficient. And maybe you don't need to do anything with your Spark application, but with another system, in this case, storage. And you can't know everything about Spark. Like with any other tool, you can't know all and every detail and every small settings that you can configure. But you can know enough to make it efficient. And from there, I would like to come to my final thought of this presentation, is that if you have only one thing to remember after this presentation, is basically it. Know your data and go with the basics. You're the only one who knows your data the most, the best, and you know everything about your data. You should know how your data is structured. You should know what kind of operations you're doing on top of your data. You are the only one who knows that. And you are the only one who can understand what is the best way to process my data and how I can process it the most efficient. And if you know your data, start with basics. Don't configure some sophisticated exotic settings. Just start with simple one and then evolve from there. It will save you a lot of time. It will save you a lot of efforts. It will save you from a lot of feelings that nothing is working and this is all horrible and I don't want to do it anymore. And again, optimizing Spark application makes it not only run faster or finish in general, but it can also save a lot of costs, execution time, and make your work more enjoyable. And I hope that you will never see out of memory issues. And I think that's it from my side. And I would like to encourage you to do a Q&A.
Perfect. Thank you very much, Oleksandra. That was a fantastic talk. And as you mentioned there, we are going into a Q&A. So if there's anyone watching along at home that has questions, please do put them into the Q&A feature. I think I started off at the start of the talk in the intro by saying, oh, I'm looking forward to this one because obviously I used to be a DBA. But I'm definitely showing my age because it was very much, working with relational databases and Microsoft SQL Server, and the data world has definitely changed over the years. I guess I'll kick things off with a question that I was pondering just as you were going into the talk there. And it's obviously a lot to it. There's, it can become a complicated environment with lots of variables that can be changed, and optimizing applications in this type of environment. It clearly is you have to know the data, you have to know the environment. So, I guess my first question was, where do you start? How do you start with optimizing Spark applications? And what should the first step be?
What I think it's a great question because it's something. Starting is always the most difficult part, at least for me. I do the following. First of all, I just try to examine the code of my Spark application and go to active run of the Spark application in Spark UI. This is the first step to give me an impression of what this job is actually doing and what I can derive from there. Knowing that, the next step will be, of course, knowing the data. You go to see what data you're working with, what is the volume, what is it a wide table with a lot of columns, or is it a narrow table with just insanely big? So know a little bit of that. When you know these two components, you also, the third in this equation is your environment where you run in this job application, or this Spark application. When you know these three things, you can actually build a strategy what should be optimized and what can be done better. But first of all, know your data, know the processing that you put on top of the data, and know environment in which you're running this application.
Perfect. Yeah, thank you very much. Yeah, as I say, it does blow my mind a little bit, and I guess a follow-on question that's come in there from Noor. So Noor, first of all, great to see you online today, Noor. Noor is from more of a data scientist background, and Noor's essentially saying, what is the best way for a data scientist to get started with using Spark, please? Is it sensible to use Python, or are there longer-term advantages to using Scala? And I know you highlighted in your talk there that certain instances Scala was definitely more performed better. So yeah, where would you recommend for data scientists to start with Spark, and what's your view longer term in terms of Python versus Scala?
Great question, because it's always this battle between Scala and Spark, Scala and Python. Scala and Python performs exactly the same way in Spark. It doesn't really matter if you run your application in Scala or if you run your application in PySpark. The significant difference comes with UDFs that I mentioned during my talk. There, it can be some difference, and sometimes quite impressive one. But if you are just leveraging Spark framework and Spark functions, Scala and Python perform the same way. For data scientists, of course, Python is more preferable because a lot of packages are already written in Python. So in a lot of cases, it's more natural to use PySpark rather than Scala API for Spark because of these packages that you would like to use. And especially if we go to a direction of machine learning and distributed machine learning, of course, Python will be your targeting language. But one more time, to summarize, it doesn't matter is it Python or Scala, it matters for UDFs. Okay, makes sense. Okay, thank you very much for that. Just as we're moving on to the next question, Hamad and Phil both in the chat saying thank you for the talk. It was really helpful. So thank you for both getting in the chat and saying thank you there. There is a couple of questions coming into the chat as well. If you could please use the Q&A feature for the questions, that just helps things on the back end for us. In terms of the next question, there's a question there. If you open the Q&A, actually, Oleksandra, you'll be able to follow along at the same time. Question there at the top from SS. So SS is using their acronym today. Their question is around user-defined aggregate functions. What is your suggestion in terms of using Spark user-defined aggregate functions in Scala, especially in terms of performance? Are these being deprecated? I don't think they're deprecated, to be honest. But now when you're asking about deprecation, I start doubting myself, but I don't think they're deprecated. But again, performance, most of, how to say it? So everything besides pure Python UDFs has quite a lot of performance gains. So if you're using, oh, it's answered. Sorry, it moved away from me.
Oh, sorry, that was me. As you were talking, I'm clicking buttons. So yeah, just carry on.
No. It's all good. So if you're using Spark UDF, they're performing quite well. The problem is that if you're basically what I wanted to address, if you're using a pure Python UDFs, like plain Python UDFs, even not pandas UDFs, so they are quite dangerous. If you're using Spark UDF, you can still, especially in Scala, you can still get a lot of performance. But again, one more time, this is a performance in on generic examples. It might differ for your particular use case.
Perfect. Thank you very much. Thank you very much. We're going to go to the question now from Nikos. Nikos' question has come through in two parts, but it's essentially one question. So the first part, he says, thank you very much for the presentation. Always really encouraging to see other professionals sharing their experience with Spark and how they handle the difficult task of using it efficiently. A little bit further down, there's a follow-on to that. So what he's essentially saying, in quite an unstable environment of frameworks, do you believe that Spark will be the go-to big data framework for the upcoming years?
I do think so. I think that Spark will be still widely used in a lot of environments. And especially now when you have significant boost of Spark usage in machine learning, because there is frameworks for distributed machine learning on Spark. And I think it will be used especially because it allows you to combine ETL processing and machine learning in one pipeline. So you don't need to do it separately.
Perfect. Thank you very much. Again, if you're following along yourself, Oleksandra, there's a couple of questions there at the top from Caroline. So Caroline Zimmerman, thank you very much for firing in your questions. First question there, have you got any advice on when you would use UDFs?
First of all, when you have specific, if we're talking about Python, you have specific libraries that are only available in Python. You basically don't have any other choice except using UDFs. Also, you can still use UDFs. It's not that you're forbidden and should never use them. Just be aware of what kind of performance difficulties it brings to you. And if this is an acceptable level for you, then please go ahead. But just be aware of that. And of course, I personally use UDFs for some things that I can't implement in Spark DSL, so with Spark functions. Then I put it in UDFs. So I a little bit go from the pure software engineering practices that everything should be a small, separate testable block of code. But I put some things that I can't do other way.
Okay, yeah, that makes sense. Thank you very much. Next question there again from Caroline. I'm breaking my own rules here, Caroline. I'm answering two questions from the same person back to back. But Caroline's asking, is Spark SQL sufficient if you don't want to do data science?
Spark SQL is a great tool if you prefer a SQL flavor. And underneath, it still will be translated to the same Spark operations if you just use a PySpark or a Scala API for Spark. So from performance perspective, it will be the same. It's more suitable for developers who like SQL as a dialect. And of course, it's not only for data science. It's you can write the whole ETL pipeline with SQL. And if it's your flavor, if you prefer SQL, then just go ahead. It will be the same performance, and you will get your work done.
Perfect. Thanks, Oleksandra. Next question down there from Hamad. I'll kind of expand on it a little bit, but I must admit it was one thing that when you were talking about partitioning and you're talking about understanding the data to know how to partition it, etc., etc. Is there a way of using an analysis tool or monitoring the data or monitoring the type of queries that are most typically run to then aid you with the performance tuning? Is there any analysis tools that you suggest?
It's a little bit difficult question because there are quite a lot of work in this area, especially with open source projects for data monitoring, and there are quite a lot of commercial projects for that. But I personally haven't seen any tool that will actually help you to, for instance, partition your data.
Okay.
You can get insights from whatever tool you're using for querying your data, to analyze just the queries that you perform, and you can understand which queries are performed more often and on which fields. Yeah. It can help you, but I can't recommend any specific tool for that. I think this area is quite in the development.
Okay, thank you very much. Next question there from Karen. How can you tell if a job is running too long? How would you know if the runtime is acceptable? Are there acceptable times based on type of data, amount of data, what you're working on?
It's a great question, but unfortunately, the answer is
there
is no answer. There is no ideal time to run, and I think that you just need to know your data and also your cluster configuration restrictions, because ideally, in ideal world, if we have all the resources in the world, we will be processing our data in a milliseconds and it will be all done. But we are working in an environment where we have too many conditions. So first we have like cluster restrictions, then we have data sizes that we are working on, and then we have an acceptable time for us.
Perfect.
What I know for sure is that main question should be is not if this job is running too long, but if this job is running too long comparing to how long it ran yesterday.
Yeah.
So this should be a question that you should be asking yourself. And if this time is different, then maybe it's something you need to investigate or something you need to pay attention to.
So is that something that you do when you first roll out a new environment? Do you kind of take a baseline and then monitor it over time, essentially?
Exactly, yes. And it's also a question of what is your acceptable time. So for instance, I want this data to be processed in a second, or I want this data to be processed before 6 a.m. It's just different requirements. Okay. Yeah, and indeed, you start with a baseline.
Makes sense. Thank you very much. A couple of comments just coming in the chat. Rafael Rakowski, thanks. Oleksandra. Camilla Varo, thanks. Enjoyed that a lot. With a clapping emoji as well. So that is like an actual round of applause. So it's just a couple of final questions. I'm a little bit conscious of time, but we'll take these two questions from Phil and Caroline. Question from Phil Allen. Thanks for joining, Phil. Is there a style of writing UDFs whereby you avoid opaque serialization and data stays in tungsten? So is there recommendations in terms of writing UDFs?
Well, you will have always serialization issue when you have a UDF in Python, and because Spark is Java-based, JVM-based language, that's why you always have this serialization. But if you write your UDFs in Scala, you still have serialization, but this is serialization JVM to JVM and not Python to JVM, so it's less time consuming.
Perfect.
And that's why you can also influence serialization. I didn't touch it into my talk, but there are settings how you can define different serializers for your Spark configuration. But in any case, you don't need to focus on serialization that much, besides just knowing that it exists if you're writing with Python.
Okay, thank you. Final question, and then we'll start to bring things to a close. And I'll get to a few more of these comments saying thank you just after this last question. So question from Caroline. My question is around UDFs, and it's basically, can you get away with using them very little so that you don't have to learn Scala?
You don't have to learn Scala if you don't want to. I think it's a great language, but you don't have to do it if it's not your cup of tea. Okay. Spark itself performs the same way if you write it in Python or in Scala or in R or in Java. It's exactly the same. It will be translated underneath in the same structures and performs the same way. If you don't want to write it, you don't have to write it in Scala. That's why you have these different flavors. Things that you need to know that if you stick with Python UDF, try to at least use Pandas UDFs, because they are a little bit more optimized in terms of how data is sent, and you can reference you can Google this information, and it's a little bit better in terms of performance, and in some cases quite better. And try to use UDFs only when you actually need them. So I think it would be, at least for me, it's what I follow. And again, you don't have to write it in Scala. You can still stick to Python. Just be cautious about what you're doing and how.
Perfect. Makes a lot of sense. Makes a lot of sense. So, well, thank you very much, man. We've fired through 10 questions there, which was a bit rapid fire. And we've had a number of comments coming in. So I will get through a few of these for you as well, because it is a bit funny in a virtual environment, isn't it? So Caroline Zimmerman, great talk. Thank you. A number of exclamation marks there from Caroline. So thank you for that, Caroline. Gowrie saying thank you. Jan, superb presentation. Well done. And thank you. Chris, many thanks for sharing this information. So I will round things up by saying a couple of thank yous. So obviously, thank you to you, Oleksandra, for giving up your time, preparing the presentation. I know obviously you've given up the hour to be with us now, but there's more involved in it than that, isn't there, in terms of being ready to give a talk. So thank you personally very much. Thank you also to Databricks. As I mentioned at the start, it's great to have Databricks partnering with us over the next 12 months. And we look forward to hearing more and more from them. And you never know, we may even get the chance to have you back later in the year, or if you do find yourself in the UK, perhaps at one of our live events as well. So yeah, I'm going to draw things to a close now, but thank you very much, Oleksandra. Thank you to everyone that joined at home, and I hope you had a good time.
Yes, I would like to say thank you to you as well, and all attendees, and the great questions that you ask. It's just amazing. And thank you very much for listening to me for 1 hour. And thank you for your 1 hour of time. And I do really appreciate it.
Awesome. Well, thank you very much. And thank you everyone for joining at home. And we'll see you hopefully next week for a new month at the Data Science Festival. Thanks, everyone. Goodbye.
Bye.